Louisiana is known for its vibrant culture, food, and weather, but that same humid, salty, storm-prone environment creates big challenges for the aerospace industry. Corrosion is a constant problem here, especially for aluminum and magnesium alloys, two of the most widely used metals in aircraft manufacturing. High humidity, salt exposure, and frequent storms accelerate the corrosion, leading to wasted materials, costly repairs, and higher dependence on new metal imports.
Local recycling and alloy reclamation facilities also struggle because corroded metals are harder to reuse. That means tons of valuable aluminum and magnesium go to waste every year, literally. So our goal is for this project, it was clear, to develop a stronger, lighter, and more corrosion-resistant metal alloy so that it can withstand Louisiana's harsh environment and last longer.
We started by researching how different alloying elements affect aluminum's properties. Elements like copper and zinc can increase strength, but they actually reduce corrosion resistance, not ideal for wet and salty climate. After reviewing the data, two elements stood out, magnesium and lithium. Both increase strength and corrosion resistance when added to aluminum, but lithium has an extra advantage. It's lightweight.
By adding just 1 to 3% of lithium, you can reduce aluminum's density by up to 10% and increase the stiffness, or the motor elasticity, by around 6%. That's huge for aerospace application. A lighter, stiffer material means better fuel efficiency, higher payload capacity, and fewer emissions. And because lithium can also enhance corrosion resistance, aircraft structures can last longer, even in Louisiana's extreme weather.
We decided on a aluminum 270 lithium alloy, which has a base of 270 aluminum with about a 1.2% lithium added. That small change reduces the material's density by about 3% and increases its stiffness by 7.2%. It's a strong, lightweight solution tailored to corrosion-prone regions like our own.
So how do we make it? It starts with alloying aluminum and lithium and trace elements. Then the material goes through several key stages. Step 1 would be casting and homogenization. It's heated to about 530 degrees Celsius for an hour, allowing the metal structure to become uniform, made of small, strong strains. Step 2 is quenching. It's immediately cool, locking the structure in place and preventing large, weak grains from forming. Step 3 would be rolling, which the alloy is cold work by rolling, which hardens it and redefines its structure. Step 4 would be precipitation hardening. It would reheat it to around 150 degrees Celsius for several days. This step forms fine precipitates, tiny particles that block dislocation, movement, and dramatically increase strength. The most important of these is the aluminum lithium and aluminum copper lithium phases, which give the alloy its superior strength and corrosion resistance. Step 5 would be cooling. Firing the material is air-cooled at room temperature, completing the process.
Based on the composition of 2070 aluminum with 1.2% lithium, the microstructure is defined by these key strengthening precipitants. The aluminum lithium and aluminum copper lithium phases during heat treatment and aging, and they're crucial for the alloy's performance. The manufacturing process is designed to maximize the formation and even distribution of these particles, ensuring peak strength and stiffness. Although we couldn't find a specific phase diagram for 2070, research shows that lithium changes the phase equilibrium of traditional aluminum copper alloys, improving both density and stiffness. With these microstructural improvements, 2070 aluminum lithium alloys reach yield strengths around 415 megapascals in the 108E57 timber, with better fatigue and corrosion resistance than traditional aerospace alloys like 7050 aluminum.
For the results, a metal is lighter, stronger, and more corrosion resistant than traditional aerospace alloys like 750 aluminum. With yield strength of around 415 megapascals and excellent fatigue resistance, this alloy is built to last in Louisiana's humid, salty climate. Longer lasting alloys means less waste, fewer repairs, and lower long-term costs, all while supporting sustainable in the state's aerospace industry.
By combining advanced material science with Louisiana's environmental challenges, we're creating aerospace alloys that last longer, perform better, and waste less.
Even though the aluminum's lithium alloys cost more to produce, their durability, sustainability, and reduced maintenance make them a smart, long-term investment for Louisiana's aerospace future.